morning, good morning. So I assume you have a question on why we have this very dapper whiteboard right here. Well, what we're switching from is the normal paint um, application that we were using to now working with Notion actually, and we are embedding a whiteboard onto our page so we can take notes inside of here and draw if need be. So it's going to be wonderful for all of our functionalities, and I'm ready to get started if you are. So, first things first, where did we leave off, right? Oops. Where did we leave off? We had discovered how to work our training model, right? Now, we know this works here, but we aren't very familiar or sure with why exactly it's working. So what we're gonna do is our same old, our basic method of stepping through here line by line. And as we step through line by line, we're going to figure out what each line is doing, what's the what's the inputs, outputs to each function, and how it all wraps up in the end to something we can compress mentally and recreate in our own way. So starting for here, starting from up here, we are freezing the backbone, right? So let's whip out our notes. First, let's start up with what is a backbone. What is a backbone to a model? So, in my understanding, the backbone refers to the feature extracting network, which is used within the deep lab architecture. The feature extractor is used to encode the network's inputs into a certain. Ooh, music is bumping right now. Hold on. Let me verify real quick. Music, sorry. 1 second. Alright, I do believe that's a lot better. Uh, just waiting for my voice to go through. Alright, I do believe that's a lot better. Yep, perfect. So, first of all, let me. It's 1:30 here, and I'm halfway home. Okay. So, the Deep Lab frameworks wraps functionalities around this feature extractor. By doing so, the feature extractor can be exchanged and a model can be chosen to fit the task at hand in terms of accuracy efficiency. So the backbone might refer to models like ResNet, which is what we're using, and it's not a universal technical term. Okay, but there's no backbone of a neural network in general. They're describing a neural network architecture, feature extraction, a part of the network that sees the input. So this could be the ResNet 18 model. My this part. in question is crucial to the overall method. The backbone is a term used in the lab models papers to refer to the exact feature to the feature extractor network. Okay. So why am I freezing the feature extractor network? Why? Like, let's kind of think about it first, come with our own hypothesis. Um, and freezing the feature extractor, what are we looking to accomplish? Right? What does the feature extractor do first? Is what we would need to know. Feature extractor is a process and machine learning and data analysis that involves identifying and extracting relevant features from raw data, which is what we're doing by finding, on our cornerback receiver imagery, you are getting the forward lean, the foot separation, the positioning on the field, things along those lines. So let's see how it works. Curious.
Hi friends, today we are going to see one more concept, feature extraction from the machine learning. Okay, a combination of
And feature extraction new features are created from a combination of original features. Okay.
original features. So features partition max means one feature and creates export new feature, new during high output. Okay, these are my existing columns, features. From these existing columns, instead of taking height and weight, I am going to create one new more column that is BMI. So how will you calculate the BMI? If you know the height and weight of the person, you will get the BMI. Okay. Now how I created this new feature. So this is a combination of height and weight, which are the original features. Now I'll consider. So instead of three features, now how many features I have? BMI and BP and output column. So my features are reduced. I have extracted the new feature from the original two features. This thing happens. So to combine these two, we can use any of these operators. To combine the original features, we can use any three of these operators. For the booleans, we can use conjunction, disjunction operators. For the if you are having nominal features, we can use
So here's something that's kind of what I could see this is, right? If we were to look at it along the lines of saying, okay, you have, let's say you want to guess somebody's weight, right? So you have a person and you have a picture of this person, right? And inside of this picture, you're going to have different features, right? You have your right arm, you have your left arm, you have your right leg, you have your left leg, you have your head. So each of these features in themselves will exist, right? And if, and let's say the body as well, right? As each of these features exist, what you can do is kind of combine all three of these into one feature of upper body. Let's call that upper. And then afterwards, you can take these features and combine them into your lower body. So you have your features extracted and then combined to be able to then combine these two features and then get you your output of your weights. Right. So to me, can I not make this bigger? To me, that makes a lot of sense. Um, so that's what feature extraction is doing, right? But the question still is, why are we freezing feature extraction? Why do we not want this to happen? Right? So what I just do? I just did something. Uh, how or why? So to me, I'm now saying, okay, we have feature extraction, but for some reason specifically, we're attempting to freeze that. My assumption would be you already have features in place and methods of extracting them. And by freezing it, we keep that as is instead of possibly messing with that process that's already pre-trained and pre-created based off that ResNet 18 model that we're working with, or default template, right? So why would you freeze feature extraction? So freeze feature, wait, no. Choose the right layers to freeze when fine tuning. Oh my God. Freeze and unfreeze effectively allow you to decide which specific layers of your model you want to train at a given time. Oh, okay. Not only, so you're saying, okay, let's say we have three layers, um, visual representation, we might as well, right? So what we're saying is, let's say we have one layer here, one layer here, and then your two outputs, right? So let's say we get this inputted, but then we don't want to change this on the back prop, right? As the output layers go to pass information backwards, let's say we don't want to touch this hidden layer. We want this to be, I guess you can say, a constant, right? What we do want to change is this first input layer, which will have its weights connecting to that hidden layer. And this is what we want to focus on for whatever reason, right? We could then freeze this hidden layer and then keep this unfrozen, this first layer. So when the back propagation starts to happen, it recognizes, okay, this is supposed to be frozen. And then this is okay to update specifically. Unfreeze will unfreeze all layers of your model. So you'll be training the earlier and later layers, although you still may be training the different layers. I believe this is done because we have to use transfer learning, and the early layers of our model are already going to be well trained to doing what they do, recognizing basic patterns. The later ones, which are more specific to our exact tasks, like identifying an animal breed, would need more training. You're smart. Freeze will set all of your layer groups except the last one to be untrainable. Except it appears from documentation that this means we freeze the first layer group, the one that comes from transfer learning, and unfreeze the second, also last group to train more. If you know the details of your architecture and want to do something in between unfreeze freeze, which specify which layer groups you want to freeze, what you want to train. Okay. So it gives us flexibility there. So why am I freezing the backbone? Okay, so it's saying freeze the neural network of the ResNet 18. I'm freezing all of that, and then I'm only training the last layer since it's such a tiny data set, is what I'm understanding. But the second question for me is this All right. My theory here is this model.fc is what we're creating, fully connected parameters, and it's requiring gradient descent. So it requires, yeah, gradient. So it's going to work with the backprop, whereas this is saying false, so the rest of the layers aren't going to work with the backprop. That's my guess. Each parameter tensor, weights, bias has a flag. Each parameter tensor, each parameter tensor, weights and biases has a flag. Should PyTorch compute gradients for this tensor during exactly. That is exactly what we guessed, and it was right on point. Perfect. True parameter can change. So it's saying, are we requiring PyTorch to update the weights using gradient descent? Iterates over every parameter in the model. The parameters are essentially each layer, right? Do not compute gradients for any of these. Results, backbone convolution layers, batch norm weights, everything is frozen at this point, nothing can learn. Re-enables only for the final fully connected layer. Results, model.fc can learn, everything else stays fixed. Okay, keep in-edge ImageNet features intact. You only learn a simple linear separator up top. This dramatic. This is called transfer learning. Okay. So what we're doing today is transfer learning. So a backbone. See, if I'm being honest, this still isn't necessarily what we're looking for. Unless we do it like this. I wish I could show you. Here's an example of what my notes would normally look like. So we say, okay, backbone, right? So you have a backbone, and I'll, give you a hyphen. And what most people would do in this situation is say, well, a backbone, blah, 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 right? To me, this is inefficient. To me, this really stunts your learning speeds and learning capabilities, even. What I find to be a lot more effective is to say backbone, and then we're saying, well, ResNet 18 is the backbone to, let's see here, my AI. And then when I see this, to me, I'm gonna see ResNet 18 and be like, oh, okay, the pre-trained model, the neural network there, to that's essentially backing the overarching application is what the backbone is. So when I see this, I can just rationalize the picture and then come to it gives you a deeper understanding. You're forced to have a deeper understanding of what's going on because you have to make it as a visual image in your own way, right? How do you interpret this to be able to visualize it? Because if you can visualize it, you can create it. You know, that's one of the biggest things for me is like, if we can visualize this, right, this house right here, we can make this. And then the more you visualize, right, the more you create, the more you put together. Not sure. I think it'll be more like that, right? Now you can make this. And then if I were to draw a table on the inside and then some windows, right? Window here, and then it's like who knows, right? Some type of awning over here. the more you create, where your car goes here, this is a car, just trust me. This becomes more akin to reality in the sense of now if I say, okay, I want a house, I can I can make one out of this schematic here, right? Obviously, there's more to it. Obviously, okay, how's the electricity going to work? What are the supports like? But it's the same concept. If I were to then visualize the electricity flowing through here and pre-plan everything, then I can just recreate this based off what I visualized and move on from there. So why would the same thing not work for taking notes for learning new topics, right? Okay. So this is what a backbone is to me. And then from here, we are looking at the, yeah, we're back here. Should it? So let's go ahead and, oh, transfer learning. That's what it was. That's what it was. So you have transfer. You know what I'm gonna do actually? Let's do this. We're gonna kind of get the best of both worlds because we're taking up a lot of space writing the names. One, backbone, right? And then we'll have two, transfer learning. And the way that I want to express this on the board would be same concept. Come here, you say, well, one, you have the backboard of res 18, and there's the backbone to AI, right? Boom, you have two. And transfer learning is uh you have your, really you could say ResNet, right? And then you say I have input layer here. These are my layers, right? These are all my layers. And then we're gonna have a frozen final layer, which, oh, sorry, no, actually, let's redo that. And this is where, to me, this is where it shines, right? Because I went and I tried to do the frozen layer as the last one, and because now have that visual of like, wait, no, 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 no. Your frozen are gonna be here, right? Your frozen is gonna be here. Your frozen is gonna be here, and then we'll go red over here because this is what's learning. Um, that's perfect. But as you see, this is us defining these concepts, these ideas, these, X, Y, and Z's without, wow, whatever. It's us doing that without without words, right? Because the words can be ambiguous, they can be vague, they can be undiscerning, but the pictures, you have to understand the concept in order to do something like this, right? You have to understand what it means to freeze the first three layers and to only learn off the last. So, anyways, besides the point. Let's continue forward. One second. Go. So first we are going to freeze to stop gradients from updating weights, which is what we're doing here. Very good. So up next we have our optimizer, and the at model.fc is what's here to say we're adding that whatever end features are coming from the model, and the output is the number of classes possible. So we're learning on that last layer specifically. Optimizer, optimizer. An optimizer is the component that actually changes the weights after the gradients are computed. Okay. So the optimizer, again, let's here. So optimizer. Um, so three. So you're going to have your node, and then your node is going to have a weight, a little bicep, and then the optimizer, which we'll call OPM or optimizer, comes in, takes that weight, and changes it. Changes it to what? Well, you still have your node, and then you still have here. Now, this weight is a lot bigger, right? So here, same concept. Now we understand the optimizer is changing the weight to the node, right? So where the optimizer sits in the pipeline, training loop logic is always. Training loop logic is always is huge here. So as long as we understand this, we're essentially so you start with the forward pass. That commutes to the logic. We know that like the back of our hand at this point. You get the raw probability score. From there, you run some type of loss function. So we're using the cross entropy loss function on ourselves, which will get us to apply this softmax log function. And then after you get the loss, you work with a backwards pass using the loss and computing gradients for what is required to compute a grade or a grad. As we have set up, it's only going to be the FC parameter. And then after that, you actually use the optimizer itself to update the FC parameters. So Atom is a smart gradient descent variant. Okay. It's kind of low. Plain gradient descent would do W whatever this is. Uh, we'll determine in the future this is valuable because for us to have gone through everything and not seen something like this before, It might be a one-off. We'll see. So Atom does more bookkeeping per weight, tracks the running average of gradients, tracks the running average of squared gradients, applies learning rate per parameter. That's important so that we're not skipping over something we may have hit. Each weight gets its own step size. Okay. Why Atom exists. Gradients and neural nets are noisy, different scales across layers, unstable early. So Atom is helping. So Atom is out of the Torch Optim module, library, whatever. And Atom is essentially just helping the consistency of dealing with loss and gradient descent and updating those weights and values. So Atom is just making this process a lot easier. Right? Atom internally stores for each parameter the parameter tensor itself, its gradient, first moment estimate, second moment estimate, time step counter. Gradients from previous batches pile up, updates become wrong, this only affects the gradients. Okay. So Atom, I do want to figure out what this 1R parameter. So Atom, long story short, is assisting with the calculation and computation of gradient descent. So you have the learning rate is okay, it's not 1R, it's LR. Um, is the learning rate step size so that we don't overshoot the minimum exactly because we want to get where that slope is zero going from either a yeah we want where y or sorry where the slope equals zero, and in order to get there it's necessary for us to find a negative slope and then keep going down on that negative slope until we get to a what's it called? I forgot what it's called at the bottom. We get to the bottom, but the bottom location. Training works, but it's pretty slow. If it's too large, you start skipping over. Okay, so we are setting the learning rate, and because the optimizer is what's changing the weights, so based off the learning weight is what's going to determine if we change the weights gradually or with big jumps in between. After that, you create your criterion, which is your cross entropy loss function. We already are familiar with that. Epochs, essentially, how many times are we going to run this? So then you start with, well, your model.train. Does not train the model. It switches the model into training mode. That's it. Here's exactly what that means. You know what? I wonder if mine simply didn't work because of not I didn't have first I think I need to freeze the backbone for sure. I also think that I need to have the model in train mode. Um so let's do that real quick. Right. You came here. We say we create our we need this, we need this. Um we already have that created so we can actually let's delete this. And let's get that there. Do this real quick. So what I'm thinking is to do something like model.train, right? So we kick the model into training mode. Actually, let's do this up here. So we put the model into training mode, then we send the model to device. Then we pull the first batch. We create the logits, create our predictions based off of that. And then your trues prediction, we put them inside of the array, print out if it works, see if it's matching. It's a after that, you create your optimizer object, you set it to zero grad for some reason. Why would you set the optimizer to zero gradient? Does that mean you're not updating the weights? Setting optimizer to zero. Need to freeze the backbone. For P, model parameters. Let's put this up here actually. Before I start training it, do that. Okay. It clears old gradients so the next update is created. Okay. So we want to do this, create the object, clear the gradients, create the criterion, run the loss function, send it backwards to what's not frozen, and then step through to update the weights, save that to the file, and then everything should be good. So let's first create the file here. Boom. And then now we can load that file while we keep running through the training. Let's go ahead and run this about 30 times, right? By the end of this, we should technically be getting pretty much everything correct. Um, Not seeing anything too. Uh, um, yeah, still not. Okay. So that did not work as expected, which is okay. It didn't work as expected, but I expected it to work if that makes sense. I don't need this. Okay. So just for a sanity check, let's go ahead and run all that. Do I need the model to device? I already did that, right? Yeah. So I don't need this necessarily. Model. What it might be is so this trains and then it updates that. So technically, I should be able to say, boom, load that, and then just run this, right? And don't even worry about updating anything. Get them all right. I see. So I need to train. I see what's happening. So, and then you run through this, run through that, run through that, run through that, you run through that, you run through that. And then for X and 1 range 30, right? Let's say this doesn't exist yet. Delete that. For X in range 30, you do this for all of them. For X in range 30, I could have sworn it was like, can't, there we go. For X in range 30, you get the next chunk to train. You train, then you're updating the gradients and everything. And then only at the end of it all do we then send it to update. Let's make sure we're going to take it there, put it in train mode, and let's give it a run. Okay. As you can see towards the end, it starts essentially getting right for the most part. So now, if I were to say, now I just want to test, right? I don't want to update anything, so we don't have to save. Just curious on testing with the new file. This is right. This is almost right. This is wrong. This is right. This is doing a lot better overall though, right? Just in general. Again, we don't have too much data. Let's try 10. And then for 10. Okay. All right. So let's train on this. Okay. So boom. Let's do that. Let's do. We don't need this. Oh, I wasn't even loading the state. Okay, hold on. So let's kick the training off, right? And it's gonna do 10, 30 times. Then this will save over. Then now we want to load the state, and then we don't want to update this. So we're just loading and seeing what happens. See if we are matching as we should. Hopefully. 1 1 0 0 1 1 0 0. Got one wrong. So we're 90% here. Um, here we are 90, 80% here. Okay. So let's do this again, right? And see if we can get even better. And again. All right, we're loading. And then we're updating 80%. Right? I think this is pretty good considering, let's say we take this off and we save nothing and we just say, okay, run it as is. What does it look like on a normal basis? Right? One wrong, two wrong, three wrong, four wrong. Right? You're looking here, you're saying one wrong, two wrong. Okay, looking here, you got one wrong, two wrong, three wrong, four wrong. So consistently, one wrong, two wrong, three wrong, four wrong, five wrong, versus saying we'll learn Let's go over 100. It's gonna take a while. I'm gonna be back real quick. Water break, and we're gonna be come back, take this out, and then based off of where that saves, we'll reload the state dictionary and then see. Oh, it's done. So now we can load. We don't need to update. And now let's just see how many it gets right. So you look in here. Oh, oh, it's pretty much perfect. It's essentially perfect at this point. Wow. Okay. 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 Now we also have this untrained data, right? This is going to be silly, but what I can do now is check. We're going to iterate over the validation data loader. Validation data loader. And we'll go two at a time. And we'll do this to two. And now let's train that. Um, that's not good. Because you have wide receivers and you have cornerbacks, right? So it should be able to go either way. What else am I missing? Training data dot classes. It's the same as the val data dot classes. What am I missing? I'm using for X next iterate out of the validation loader. You're taking a batch of two. So, huh. Like as much as I want to sit here and act like, yeah, they're all zeros. I just find that hard to believe. Okay. Oh wow. All right. So I'm I am loading and there's no shuffle on. Hold on. This is my guess, right? No, this is the true, and then this is my guess onto the true. Yeah, let's try this. Just so I could see something a little different, right? Okay, now it's completely different. So let's print out my predictions. Or print truth, truth, and then let's print out pred. And now we can see side by side. Wrong here, wrong here. Got it right here. Got it right here. Got it wrong here. This is for unvalidated data. This is pretty decent, right? I don't know, honestly. But what I can say is it's probably a lot better than if I were to just have it like this. Um, take away that. If you look here, wrong, 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 wrong. One right, wrong, wrong, right. I mean, it pretty much ends up being 0 0 for my predictions pretty much every time because it doesn't understand what's going on, right? But if I say training, again, training data loader, right? Training data loader. And then we function off this. We want to save our model after it's done training. Let it train 100 times. Okay, now water break. All right. So now we have our trained data. Come here. Don't need to update. And let's take a look at the validation data, validation data loader, and see how we do. Oop, it's a lot of iterations, but whatever. Uh, right, wrong, right, wrong, right, right. Yeah. Okay. I mean, it's pretty much clear. We can't really. I don't see a way we can disagree in the fact that this is learning, this is training, and now we understand what we were missing. We weren't in train mode, and I don't think we were doing anything with the models either. So that we weren't actually saving them. We were saving the models, but we weren't updating them properly. What we were doing was we were running and then re-uploading to the model each time. So although we would, you know, train 10 times, we would then update that model with a new run, with a new run of the entire program. But now we're running our X amount of times, we're running 100 times, and then updating with one that's been ran 100 times. So I assume, you get to the points where you run probably this 10,000 times to get things updated, or million, 10 million times to finally train everything. Wow. One of the very interesting parts about this is the ability that I've gained to be able to just speak during everything that we're doing. I'm not stopping and having to think because like we've done this. We've built our foundations. We understand what we're trying to do now. Now it's how do we make it work for us, right? So we understand now how to train the model. Next up is let's start actually doing what we're here for. We've learned the tool, how to create the tool, how to edit the tool and make it work for us. Now it's how do we get better results, um, and things along those lines. So next up for me is I think we're gonna dive into Notion. Next up for me, we are gonna dive into day 19. We are going to dive straight into. Hold on, this is code review, right? Code review. That's not how you spell review. Day 19 is 100% going to be um, tracking training. Right? The same way they had their laws, their loss and stuff like that, and the correct prediction and all this good stuff right here. This is the same exact thing. The accuracy, I'm gonna start working on that as well. Tracking training. So next, accuracy, loss, etc. We're going to get that next. So uh that is all I got for today, and I hope you guys learned something. I'll see you on the next one.